Welcome to AI Paper Slap. Let's just jump right in. Today we are looking at the Qwen-RobotWorld technical report. It's titled Unifying Embodied World Modeling Through Language-Conditioned Video Generation. This is from the Qwen team, released June 17th, 2026.
Yeah, and it's an absolute monster of a paper for the embodied AI space.
So for the listener, let's hit the core insight. Give us the 30 to 60-second breakdown. What did they actually do here?
Right, so the big bottleneck right now in embodied AI is fragmentation. Every single robot needs its own bespoke control interface. Joint angles for one arm, end effector waypoints for another, steering commands for a car.
It's all highly specific hardware code.
Exactly. And what Qwen-RobotWorld does is solve that fragmentation by using natural language as the universal action interface. It's this massive double-stream diffusion transformer that predicts physically accurate future visual states across everything. Robotic manipulation, autonomous driving, indoor navigation.
And it's not just making pretty pictures, right? It actually adheres to real-world physics.
Perfectly. Literally a 1.000 physics adherence score. And because it's a unified model, it enables these wild capabilities. Like you can take a video of a human hand doing a task, and it translates that directly into a photorealistic video of a completely different robot arm completing the exact same task.
Zero shot. No hardware-specific coding required.
Zero shot, yeah.
Okay, if you're an ML engineer building robotic systems right now, you know the absolute nightmare of hardware-specific representations. So to really grasp why this natural language approach is such a paradigm shift, we kind of have to look at the two major dead ends the industry has been hitting.
Yeah, the two main extremes in world modeling.
Right, so on one side you have your purely visual models, things like Sora 2 or Veo 3, and they generate absolutely beautiful, temporally consistent video. I mean, you can prompt them for a cinematic tracking shot and it looks flawless.
They are physically hollow, like completely hollow. They learn visual priors. They know what a shadow should generally look like or how light reflects off water, but they do not learn causal physical consequences.
Right, they don't understand rigid body constraints or accurate contact dynamics.
Exactly. If you ask one of those general video models to generate a clip of a robot arm pushing a heavy metal block, the arm might just, phase directly through the table, or the block melts.
Yeah, the dreaded spaghetti arm effect. And then on the other side of the spectrum, you have the domain-specific embodied models, things like Cosmos or LVP. And these are highly tailored, very physically grounded for individual scenarios like tabletop manipulation.
But the problem there is they rely on native kinematic code. So if you train a world model to understand the steering commands and the velocity profiles of a self-driving car, that model is fundamentally useless for predicting the physics of a dual-armed kitchen robot.
Because the kitchen robot uses joint angles, the representations are just totally incompatible.
Right, they can't talk to each other.
Yeah.
Which is exactly why language is so uniquely powerful here. When you issue a natural language instruction, like grasp the red cup and lift it vertically, you are implicitly encoding the entire action sequence.
You're defining the goal state and the physical constraints all at once.
Exactly. You don't need to know the specific length of a Franca gripper versus an Aloha dual arm system.
Yeah.
The language handles the abstraction.
It makes me think of, imagine trying to write a single API that controls a self-driving car, a robot dog, and a bimanual kitchen robot using their native code. It's practically impossible because every single kinematic chain needs a bespoke interface.
It's a total engineering nightmare.
Right. But what Qwen-RobotWorld does is just bypass the native code entirely. It uses the one API that everything, regardless of its morphology, already understands, which is human language.
Yeah, by training the model to predict the next visual state purely from a text action and the current observation, the domain-specific physics stop competing with each other.
They actually start reinforcing each other, don't they? Like the fine-grained contact dynamics from manipulation and the 3D scene geometry from driving?
Exactly. Under this shared language interface, the model builds a unified understanding of reality. But abstracting the kinematics sounds elegant. Building an architecture capable of actually processing that abstract text into perfectly constrained 3D physics requires a very specific engine.
So let's look under the hood. They are using a 60-layer double-stream multimodal diffusion transformer, or MMDiT.
Right. And the architecture is split. You have a generation stream that processes the visual state. And specifically, it uses visual latents extracted by a video-compatible WAN VAE.
Just to quickly clarify for anyone unfamiliar, a WAN-VAE is a specialized autoencoder. It basically compresses massive amounts of raw video pixel data into manageable, information-dense, latent representations. So it's the visual workhorse.
Yeah, exactly. And then you have an understanding stream that processes the action, which in this case is the text instruction.
Okay, I have to stop you there, though, because I was looking at the architecture diagram for that understanding stream. And they are using a massive, completely frozen Qwen 2.5 VL model as the action encoder.
Yeah, they are.
Why on earth would they do that? I mean, wouldn't a lightweight, dedicated text encoder like T5 or CLIP be vastly more compute efficient for parsing simple text commands like push the block left?
Yeah, that's the exact intuition most machine learning engineers would have. But it misses the paper's secret weapon. Lightweight encoders are great at semantic parsing. They know push is a verb and block is a noun.
But they don't know what a block actually is in 3D space.
Precisely. They lack internalized world knowledge. Qwen 2.5 VL, purely because of its massive scale and multimodal pre-training, inherently understands physics and geometry. It already knows what a robot arm is.
Right, it inherently understands that a robot arm is a rigid body with fixed lengths and specific joint constraints.
Yes. So it's not just translating the text into an embedding. It's acting as a geometric anchor. It enforces reality.
So these two streams aren't isolated then?
No, not at all. They interact via layer-wise joint attention at every single block in that 60-layer transformer. So by using this massive multimodal large language model and coupling it deeply with the visual generation stream, the model implicitly constrains the space of physically plausible state transitions.
Ah, so this is how they prevent the spaghetti arm effect we talked about earlier, where objects deform, melt, or stretch unnaturally across video frames?
Exactly. The frozen MLLM prevents those physical hallucinations, and you don't even need explicit geometric prompts from the user.
That is brilliant. And the spatial encoding they use to achieve the multi-view consistency alongside this is fascinating. They're using an asymmetric 3D ROPE, rotor position encoding.
Yeah, this is a very cool architectural detail. Standard rotary embeddings allocate dimensions uniformly, but the Qwen team used an asymmetric split.
Right. Out of 128 dimensions, they allocate only 16 dimensions for the temporal axis, but 56 dimensions each for spatial height and width. I was trying to picture why you would intentionally imbalance the architecture like that.
What did you come up with?
It's almost like packing for a trip. The temporal axis, time is like your toothbrush. You only need a little bit of space for it because the frames barely change millisecond to millisecond. The difference between frame 10 and frame 11 is minuscule.
Oh, that's a great analogy.
But the spatial axis, height and width, those are your clothes. You need a massive suitcase for those because you have to account for an infinite variety of object positions, multi-view camera angles, and whatever resolution you are running at inference time.
That perfectly captures the resource allocation. Adjacent video frames are highly correlated, so the temporal axis simply doesn't need as much representational capacity to track those state changes. This asymmetric ROPE allows the model to scale dynamically at inference time and handles multi-view consistency seamlessly.
But I mean, a massive model enforcing reality still needs to be taught what reality actually is. You can have the most beautifully designed 60-layer MMDiT in the world, but it is totally useless without an unprecedented amount of aligned physical data.
Which brings us to the EWK dataset, the Embodied World Knowledge dataset.
The scale of this thing is staggering. They curated 8.6 million high-quality video text pairs. That's over 200 million frames.
And the mix is really deliberate. They used a 30-70 split. 30% is general world data, so internet videos, natural scenes, sports.
Which provides the foundational visual priors, right, for appearance, geometry, basic dynamics.
Exactly. And then the remaining 70% is structured embodied data spanning over 20 different robot morphologies and over 500 action categories.
Okay, but to get that 70% aligned under one language interface, they had to solve a massive annotation problem. They couldn't just look at a video and write, robot grabs cup. That wouldn't give the model enough causal data to learn the physics.
No, not even close. They had to put every single video through a rigorous 5-layer annotation pipeline.
Walk us through those layers.
So first is the task goal layer. What is the high-level intent of the transition between state A and state B? Second is the action detail layer. And this is crucial. This is where they explicitly declare these spatiotemporal trajectories and the exact viewpoint.
Right. They mandate explicit declarations like egocentric main view or wrist view. Because if the model doesn't know where the camera is located in 3D space, it cannot learn accurate scene geometry.
Exactly. You have to anchor the perspective.
And the third layer is physical feedback. The annotators have to describe the verifiable contact state changes like Did the object displace? Did it deform?
They ground the action in strict, visually confirmable outcomes.
It really is like a forensic video analysis. There's no guessing allowed. Every physical consequence has to be explicitly mapped to the language prompt.
And the output of that forensic analysis actually yields 2 different captions for every single video. You get a comprehensive description, which is about 50 to 100 words long, specifying the exact viewpoint agent action feedback quadruple.
Very dense.
Very dense. And then you get a concise description, which is just 15 to 30 words, retaining only the basic command. And during training, they sample from the comprehensive and concise descriptions with a 50-50 probability.
The genius of that 50-50 split is entirely about inference generalization, isn't it? Like, the comprehensive captions force the model to learn the exact physical trajectory and contact dynamics deep in its weights during training.
Right.
But at inference time, a human operator isn't going to type a 100-word forensic description. They're just going to type, pick up the cup. So the concise captions ensure the model doesn't overfit to hyper-detailed prompts.
Yeah, it allows it to easily execute brief, high-level commands when it's actually deployed. That balance is crucial. But teaching a model, say, a wrist view of a robotic arm grabbing a cup, introduces another major hurdle, which is catastrophic forgetting.
Ah, right. How do you teach a world model the fine-grained manipulation of a robotic gripper without it losing its ability to render general world physics, like lighting or fluid dynamics?
They solve this using a progressive, 2-stage curriculum powered by a flow matching objective.
Let's unpack that flow matching objective for the technical listener, because standard diffusion models can really struggle with cross-modal generation across varying sequence lengths.
Yeah, they do. So flow matching here uses a log normal distribution with adaptive shifting, which essentially means the noise profile dynamically adjusts based on the length of the video sequence, making the training significantly more stable.
Got it. So let's break down the 2 stages of that curriculum. Stage 1 is pre-training. Here, they train jointly across text-to-image, text-to-video, and text-image-to-video tasks.
And they use that general world data alongside human interaction priors. Massive datasets like Ego4D and Epic Kitchens, which feature humans doing everyday tours from a first-person perspective.
By learning how a human hand grasps a tool or pours water, the model builds a natural bridge between domain-agnostic world physics and embodied action priors.
Exactly. And the text-image show training acts as a visual quality anchor, ensuring the object morphology remains sharp and consistent.
Then comes the SFT stage, supervised fine-tuning. This is where they inject the embodied specialization.
Right, but they keep the general world data in every training batch at a 30% ratio, just to prevent that catastrophic forgetting.
For the 70% embodied mix, they heavily weight manipulation data, don't they? It makes up about 90% of the embodied sampling. Why tilt the scale so heavily toward manipulation? Why not balance it evenly with the autonomous driving and indoor navigation data sets?
Well, because manipulation is where the model really learns contact physics. Driving teaches large-scale 3D geometry and multi-agent dynamics, but tabletop manipulation forces the model to understand what happens at the exact millimeter 2 rigid bodies collide.
That depth of physical grounding requires massive sampling weight.
It does. And the driving and navigation data, which each get about 5% of the mix, provide the breadth. They teach the model how to scale those intricate physical rules up to room size or city size environments.
That makes a lot of sense. Now, if you are working with real-world robotic systems, you are almost always dealing with multi-view data. You've got a main over-the-shoulder camera, plus maybe 2 wrist cameras.
Oh yeah, always.
When they train on this concatenated multi-view data, do they have to build separate models or bolt on new architectural heads to handle the different camera streams?
So this is where the asymmetric 3D ROP we discussed earlier shows its true value. Because the spatial dimensions are so highly parameterized, they do not need any structural changes to the MMDiT at all.
Wait, really? No structural changes?
None. They just concatenate the synchronized camera views into a single visual latent grid. The 3D ROP inherently learns the geometric consistency across those synchronized streams.
Wow. So the model simply figures out that a movement in the main view must correspond to a specific occlusion in the wrist view purely from analyzing the data.
Yeah, no bespoke engineering, just letting the architecture learn the geometry natively.
That is incredibly elegant. Let's talk about what happens when you actually run this thing, because the zero-shot capabilities and the benchmark suites in this paper are, frankly, hard to believe.
The human-to-robot transfer illustrates the power of this architecture perfectly. They designed a 3-segment input sequence to handle cross-embodiment video editing without collecting a single frame of physical robot data for the target hardware.
Okay, walk us through the 3 segments.
Segment 1 is the scene condition. This is a video of a human doing a task, say, picking up a cup, but they use an automated pipeline to mask out the human hands entirely.
So this just gives the model the background, the lighting, and the object layout. But I'm trying to visualize this. If you mask out the human hands in segment 1, you are just left with a floating coffee cup.
Exactly, it just floats up.
How does the model bridge the gap between a floating cup and a specific robot arm doing the work?
That is where segment 2, the robot reference, comes in.
Yeah.
They take the 3D hand key points from the human video and they run them through MuJoCo.
Which is a highly accurate physics engine.
Right. They use MuJoCo to calculate the inverse kinematics for the target robot arm, rendering a simplified simulated video of the robot doing the motion.
So this render has no real lighting, no shadows. It just looks like a gray skeleton in a void.
Yeah, exactly. But it provides the flawless kinematic trajectory.
Okay, so then segment 3 must be the generation segment, the noisy latents.
Yes. The MMDiT uses joint attention to simultaneously look at the real-world scene with the floating cup in segment 1, the blank MuJoCo kinematic skeleton in segment 2, and the language instruction.
And it fuses them.
It fuses them to synthesize a photorealistic video of the target robot completing the human's task. It hallucinates the accurate shadows, the reflections, and the contact dynamics completely seamlessly.
Doing the zero shot across 14 different robot morphologies is just unprecedented. And when you look at the raw numbers, Qwen-RobotWorld just crushes the domain-specific models.
Yeah, the benchmark sweeps are definitive.
It ranks first overall on EWMBench, which measures embodied motion fidelity. Its human-to-scene distance score, or HSD, is 0.566.
To put that in perspective, that is a 33% improvement over the runner-up model, LVP.
Massive jump. It also took first overall on DreamGen Bench across all 3 robotic embodiment subsets, proving it handles object-level compositional generalization better than anything else currently available.
But the stat that genuinely blew my mind was on World Model Bench.
Oh yeah, the physics adherence.
Right. This benchmark specifically measures physics adherence. Qwen-RobotWorld achieved a perfect 1.000 score.
A flawless rating across Newton's laws, mass conservation, fluid dynamics, and gravity.
It beat all open source models and performed on par with the heaviest closed source general video models while maintaining far superior instruction following.
But to prove this isn't just benchmark memorization, they ran zero-shot tests on the Robo20F benchmark, right?
Yeah. Robo20F evaluates complex, long-horizon tasks on unseen simulation environments, and Qwen-RobotWorld demonstrated incredible robustness here.
It maintained perfectly coherent execution and cross-view consistency on tasks it had never been explicitly trained on.
Which proves that the model truly understands compositional physics. It hasn't memorized the training set. It has generalized the underlying rules of reality.
Which brings me to a paradigm-shifting question for you to consider as we wrap up. If Qwen-RobotWorld can perfectly simulate physical state transitions from text alone.
Wait, text alone, yeah.
Right, and if it can seamlessly translate human demonstrations into photorealistic, physically accurate robot executions without collecting a single frame of real-world target robot data, are we looking at the death of the traditional sim-to-real gap?
That is the million-dollar question.
I mean, if a video generation model can hallucinate the physics, the lighting, the contact dynamics, and the multi-view geometry of any robot based entirely on language, the future of robotics training might not happen in physical labs at all.
We might be generating infinite, perfect training data entirely inside the latent space of models like this.
It's a wild thought to end on. Thank you for tuning into this deep dive on AI paper slop. We'll catch you on the next one.